So here we are having question number 41. A sound wave from a source A follows two paths AOB and APQB in a tube as shown in figure. For the silence at B, possible wavelength of sound will be what? Now, two waves are there and it is telling for silence at B. So there is the condition of a specific interference, that is destructive interference. Silence means intensity, there will be minimum. So destructive interference, the question is talking about. Now, let's calculate the path difference. One wave is traveling toward APQB and the path, it is covering L plus L plus L. And path number 2, it is covering directly 2L. So the path difference delta X will be what? 3L minus of 2L, which is L. And we know very well about the condition of destructive interference. For destructive interference, the path difference must be equal to 2n minus 1 times lambda by 2, where lambda is the wavelength. Now, we already have calculated the path difference. So putting here, we get L equals 2n minus 1 lambda by 2, where n starts from 1, 1, 2, 3 and so on. So, after putting the values of n, we can get L equals lambda by 2, 3 lambda by 2, 5 lambda by 2, 7 lambda by 2 and so on. But we have to talk about possible wavelength. So we have to calculate lambda. So lambda in terms of L, we can write lambda equals 2L, 2L by 3, 2L by 5, 2L by 7 and so on. Now let us try to find out the option. 2L is not in any option. 2L by 3 is not there in any option. 2L by 5. Yes, we have got 2L by 5 as option number 2. So without wasting our time, we will go with option number 2, which is absolutely correct. Now let us proceed to the next question, that is question number 42. Here is question number 42. Velocity of sound in air is 320 meter per second. For an organ pipe closed at one end of length 2 meter, the resonating frequency may be what? Now we have to talk about the resonating frequency, and the case is closed organ pipe. We know that the harmonic frequency for a closed organ pipe is given by 2n plus 1 V upon 4 times L, where V is the speed, L is the length of tube. Putting the values, we get F equals 2n plus 1. V has the value 320, 4, length is 2. After solving, we can get 2n plus 1 multiplied by 40, where n is 0, 1, 2, 3, 4 and so on. Let's plug the values of n one by one and see the possible frequencies. So if we put 0, we get 40 Hertz. If we put 1, we get 120 Hertz. If we put 2, we get 200 Hertz. If we put 3, we get 280 Hertz. If we put 4, we get 360 Hertz and so on and so on. So we have to find any of the frequency in the option. We have to search, and if we find the option, if we look the option, we can say that 360 Hertz is there in the option. So that's why we will go with 360 Hertz. That is option number 4. So our answer will be 360 Hertz because it is present in the option and rest are not present in the options. Now let us proceed to the next question, that is question number 43. Here is question number 43. A train moving with constant speed of 40 meter per second in an elliptical path in anti-clockwise direction. blows horn at point P. An observer standing at point Q receives the horn sound of frequency 2000 Hz. If the ratio of minor to major axis are 1:3, then speed of sound in air is 320, then true frequency of the sound will be what? After looking and observing the question, we can say that the question belongs to Doppler effect, in which if there is a relative motion between observer and source, then the observed frequency will be different from the true frequency. And here in this case, the observed frequency nu will be given by V upon V minus Vs multiplied by nu naught. Now all the notation have their meaning. V is speed of sound, Vs is speed of source along line joining source and observer. Source and observer. So here in question, apparent frequency is given. We have to calculate the true frequency. V is 320. What about Vs? Vs will be this one. We are given with the speed of train, that is 40 meter per second. But we have to calculate this component, the component of speed of train toward the line joining source and observer. Ratios are given. This is 1, this is √3 we can take, and by the Pythagoras theorem, this can be written as 2, and using the trigonometrical identity, this angle comes 30 degree. So that's why this will be 60 degree. So therefore we can write Vs is what? 40 times cos 60 degree. That is 20 meter per second. Let us plug all these values in the expression. Nu, observed frequency is given 2000 multiplied by V is 320 divided by 320 minus Vs, that is 20, multiplied by true frequency, which is we have to calculate nu naught. Therefore nu naught will be 2000 multiplied by 300 divided by 320 Hertz. So after solving, we will get the value of nu naught as 1875 Hertz. And after looking at the options, we can say that option number 3 is absolutely correct. So we will go with option number 3. Here is question number 44. A ball projected from origin at time t equals 0. X and y are coordinates of its displacement. Along x-axis it is 4t square and y-axis it is 3t minus 5. So the position is actually time dependent. We have to calculate the instantaneous velocity at any instant of time. We know very well if x coordinate is changing with time as well as y coordinate is changing with time, then the speed in vector form we can write dx by dt I cap, that is speed of the object along x-axis, plus dy by dt j cap, speed of the object along y-axis. We can write differentiation of position x with respect to time gets you 8 times t I cap, plus differentiation of y, that is 3t minus 5, gets you only 3 j cap. This much meter per second will be our answer, that is 8 t I cap plus 3 j cap. After looking at the options, we can say that option number 2 is absolutely correct. So I'll go with option number 2. Now let us proceed to the next question, that is question number 45. Here is question number 45. A mass m is moving with velocity v vector along line y equals x as shown in figure. Which one is correct statement about angular momentum, about A and about B respectively? Now we have to calculate the angular momentum about 2 points A and B, and then we have to compare them. So we know very well magnitude of the angular momentum about any point will be given by linear momentum multiplied by perpendicular distance between the point and linear momentum vector. So this is the linear momentum vector, and these are the point about which we have to calculate the angular momentum. So draw perpendicular on them. This is for A, suppose RA. This is for B, suppose RB. Here the length RA and RB will be equal. So the magnitude of angular momentum will be equal. Here magnitude of angular momentum about A will be same as magnitude of angular momentum about B. This is why, this is because linear momentum is same, mass into velocity for them, and separation, that is RA, will be same as RB. That's why magnitude of angular momentum will be the same. But let's see what about the direction. Here the angular momentums are opposite. Angular momentum is a vector quantity which is given by R cross P, the cross product of position vector and linear momentum vector. And if we do the cross product, we will find both are in opposite direction. So we can write here vector LA is not exactly equal to vector LB, as they are in opposite direction. Yeah, but it is true that their magnitude is equal. So after looking at the options, we can say that we have to go with option number 4, because this is the only possible true option. If we check options one by one, LA equals LB, which is not absolutely correct. Only magnitude equal, not direction. Mod of LA not equal to mod of LB. This is not true. Their magnitudes are equal actually. Third option, their magnitude is not 0. So we'll cross the third also. Fourth one is the only correct option. That is LA is not equal to LB. So that's why we'll go with option number 4.